Today's topic is replicate. So this was a part of my PhD thesis. So we use this framework to plan infrastructure, or infrastructure systems. So how we plan is like to make sure that the infrastructure or system would be resilient, at the same time it would be sustainable. Okay. So the content is projected clean energy system installations and which source would dominate, then solar energy research that we conduct at our laboratory. So that is Sustainability and Resilience Research Laboratory led by Dr. Chopra, and why our solar PV systems are underperforming, and then how replicate framework would help in better planning, and then dynamic gray voltaic farm planning using replicate framework. So this would be the content. So for the next 30 minutes, I'll be taking to the slides. Now, if you see the projected installations capacity and electricity generation by source, so we have like various other fuels, like apart from solar, we also have bioenergy, waste, hydrogen, ammonia, and even we have carbon capture and utilization. But out of all, if you see this IEA's net zero emission 2050 scenario, solar PV is dominating in terms of installed capacity or projected installations. And even if you see the electricity generation, solar would surpass, and then followed by wind energy. So this is the one of the reason, why we more focused on solar energy apart from the other systems. But we also look at solar integrated with other renewable energy systems too. Now, if you see how the solar photovoltaic systems are installed, so up to now, as you're familiar, mostly at a material science level, we only produce PV modules. But these modules, when they come into the real life environment, they can be installed in multiple ways. So for example, if you see this first, like solar photovoltaic tree, we can install it. We can also install it as an open mount photovoltaics, that what you see like everywhere on a ground mount. Then we also have a roof mount. Then we have a building attached photovoltaics. Then we have canopy mounted photovoltaics, roof integrated photovoltaics, facade integrated, building integrated. Like, of course, like few comes under the family of BIPV, that is facade, canopy and all. Then we also have the most advanced systems called vehicle attached photovoltaics and vehicle integrated photovoltaics. These have become more popular because of the advancements that we have seen in photovoltaic cells, like a rollable, flexible, all these things with a bending radius of less than 1 centimeter have come up. That's the reason we have this advanced vehicle attached and vehicle integrated. And also we have seen the solar cells emerging into civil infrastructure, on pavement, and also we come up with the concepts called road attached and road integrated. And then we also have this locomotive mount photovoltaics. So though it is not very much popular, but it was first tested as a pilot project in Russia. And then we also have a rail track integrated, and then we also have a floating solar, we have submerged, we have like underwater onboard solar photovoltaics. So this we attempted a couple of times in exploring plastic waste in ocean seabeds. And we also have a pole mounted photovoltaics and then pole integrated photovoltaics. These have become very popular very recently because all these LED lights have become more popular on road infrastructure. So these are like low power devices, a kind of thing. So that's the reason people have started, coming up with the concept of preparing glass fiber poles integrated with solar cells. And also we have our overhead systems. So this is how the solar photovoltaic systems are installed in real environment. Now, if you see what our research, so like our group mainly is as an interdisciplinary group. We focus on multiple research areas, mostly from a critical infrastructure sector category. But here I'll be just giving you the solar wing, what we generally do it. So if you see here, we have like available PV technologies, which we generally don't work on at this stage, but we collaborate for this sort of systems with science people. And then we also see like which modules are commercialized from an industry. We collaborate with industry people. Then we collect that data. And then we try to create systems, So what are these systems? These systems are nothing but you see in our electric power system right now. So that's what we generally have: nanogrid systems, microgrid systems, smart grid systems, and virtual power plant. So the smart and virtual power plant were more related to the digitalization of the electric power system we have it. But when we see this nanogrid and microgrid, they're more like decentralized ways of powering houses. Let's say you have a remote house where we doesn't have electricity supply, then we can come up with a nanogrid concept using just having a solar on your rooftop or something like that. And the microgrid is one or more combinations of energy resources you can come up with. And then we create these systems with the existing infrastructure and for different applications. That is, maybe BIPV is one, agrivoltaics is one, and we also cover powering the desalination, then solar islands, and then the electric vehicles. And what we do is, once we create these systems, we test these systems in different ecosystems, because the same system, a BIPV system in a tropical climate, a BIPV system and colder climates would not perform the same way. The ecosystems have a different effect on the total performance of different systems. So we cover more from a systems point of view and how to integrate these systems in the existing infrastructure or plan a completely new infrastructure. So that's what we generally do it. And the applications we cover are mostly service based. It covers heating, lighting, cooking, and transportation, and other commercial facilities. And then we also recently entered into the markets, because now how we see this electric power industry is transitioning is it's not anymore conventional. It started taking up a P2P market where a building owner who has excess power can trade the power like any other commodity. So, and then we also have a shared business models, and then the energy e-commerce, because the energy e-commerce is really becoming very popular these days, because you just have a prepaid card, recharge it, and then you can get your energy. And you can even have the option of choosing which type of energy source you want. Let's say you want only energy from solar, you can still get that. Energy from wind, you can get that. So that they will accommodate, or they will account these energy resource, energy consumption from which source, to make sure whether your building is green building or not, whether you have a green energy consumption or not. So all these things are becoming popular. So that's why we cover wider research area, covering from a systems point of view. And now, so we were talking so many systems. Now let us see how the solar photovoltaic systems are analyzed in real time. So we mainly follow IEC standards or IEA standards or NREL standards. So what these three standards would tell is to have an integrated technical, economical, and environmental assessments to understand each system's feasibility at any point of time in a given site. So this is what generally we follow. But are we following this assessments or not is a question right now. Now, if you see the academic research mostly, so people do separate analysis. So very few researchers around the world will only focus on integrated approach. So many people, either they just do simply technical assessment and they just publish it, or they do economic assessment and they do it, or environmental assessment. This is what mainly happening. And then we have seen this like systems emerging as an integral part of this existing other infrastructure sectors. So when such systems are coming up, it should happen through systems thinking, but it is given less importance in the existing research areas. And apart from this, we have a wider range of simulation tools, people use it. But if we see the systems, every day a new system is coming, new integration is coming, but the simulation tools are very old. As of today, even now, we don't have a simulation tools that account for the feasibility of various systems we have seen it. So still people follow the traditional tools and then they just report the data. So this is what happening in academic research. And then resilience planning is something that's mostly ignored in existing systems. Now, if you see this industry, because now many people who want this photovoltaic power plant installation, they generally approach an industry. So what industry do is, industry would simply do techno-economics and they ignore the sustainability assessments. If I had to speak from my personal experience, because I have worked as an energy engineer in Nigeria, installing solar power plants for UNDP projects. So what we see is, even they don't really account for sustainability in a way that has to be accounted at this stage as scope 1, scope 2, or scope 3. So mostly just with some CO2 numbers, multiplying factors, they just do it. And then industry also would follow similar one tool. That's why they just give like, either underperformed or overperformed data, but that would actually differ from the actual site performance. And then even in the industry, resilient planning is like, it's mostly ignored, but if any customer asks, it will be like, added service, but it comes with too much cost. So now, like, we have seen like, how these power plants are performing in real time, So this is what we have been conducting from the past 3-4 years. So now this is the survey we did for almost all ground-mounted power plants in different latitudes around the world. So what we observed is the performance ratio is varied as per the sizes as the capacity increases, and then the yield factor is also increases. Now, like what these factors are, like mostly in science research, we only see like either a VOC or ISC or Pmax, or at last we only like see at the energy density and fill factors. But when we take these PV modules into real time, these factors would just consider as a benchmark data, as a standard testing conditions data. But those data will completely differ from the actual performing conditions. So that's the reason, the research community has come up with a concept called PR. So we call it as a performance ratio. So this performance ratio will account the total, all the factors that interfere in the lifetime of a plant. Let's say if a solar power plant installed, it will be there at least for 20 to 25 years. And if it is an organic solar cells, maybe less than 20 years. But so accounting all factors, we just estimate this PR as a 1. So a nominal PR would be somewhere around 80 to 90, but we have seen like, most plants falling under 80. So the reason is maybe they were not planned effectively, or the infrastructure was not planned in a way it should be there. And then the same happened with the yield factor. Now, if you see, the effect of simulation tools. So we did this simulation study considering a 2 megawatt floating solar power plant installed in an urban water reservoir. And we also have a similar plant in Hong Kong too. So now, mostly industry people would use any of these tools, either a PVSys, SAM, or Helioscope tools. So they use these tools and they just give the performance data, and then they estimate the revenue potentials, all these things. So with this, the client would generally say yes or no for project installations. But what we observed is when we actually collected the data from this 2 megawatt power plant over a period of 2 years, and what we analyzed is the output is completely different, either under or overperformed when compared to this PVSys. Now, when you account this actual performance, the total economic assessment is varied. So that means the cost of electricity that was guaranteed to the consumer would not be the same thing. At the same time, the payback periods would vary. So that's the reason we are saying like, we need to have a proper approach while planning all the systems. Now, we have seen a similar thing with a different parameter that affects the performance in a rooftop BIPV solar power plant. Yeah, BIPV is like building attached solar power plant. So in most of the urban areas or even rural areas, soiling is a major factor, the aerosol movement. So these aerosols will accumulate on the solar panels. Now, because of this, there is a soiling losses. So the soiling losses will directly account on the energy production itself. Now, we tested this on a soiling density gram per meter square, varying from almost 0 to 14 versus the soiling losses. What we observed is when the soiling density increases, the amount of power that is lost due to soiling is really increasing, and it might even go to 25%. So there is a huge amount of power that is lost because of soiling too. So that means we need to have an optimal cleaning. So if we don't do proper cleaning, then we will lose a lot of useful amount of energy. But the cleaning comes with a cost of priced commodity, that is water. So this is one factor we need to look into it. And then we have seen this again in BIPV slope group solar power plant. So here we just accounted the whole lifetime, the performance loss, what is happening at different stages. So what we observed is the BIPV power plants will perform a bit lower when compared to the ground mount for various reasons. So that's the reason we accounted all the parameters in 3 different stages, that is available energy in the input from the sun, then atmospheric variations that lowers the intensity. Then what we observed here is 14.38% is lost only in the energy, like from light to DC conversion itself at the module level. But this is like quite high when compared to other power plants. So what is the reason for this is like, the way we install the solar power plants or the building material heat transfer could be one of the reason, or the other building shadow could be another reason. So there are various reasons that are possible for this huge amount of DC conversion losses. And then we did another study that is on a BIPV slope-proof community solar power plant. So then what we did is we accounted exactly what is happening at a cell level. So at an array level, like in a PV array level. Then what we saw is as the temperature is increasing from 20 degrees to 55 degrees, that means the cell temperature or module temperature is raising, the performance is almost like, try to drop. So because of this, so the performance is almost in ideal conditions or in a practical conditions, it is way lower than the benchmark or the standard STC condition performance. But as the real-time conditions again affects, if still temperature goes high, the performance is slightly dropping. Almost it is becoming as 11.60% efficient. That means if a manufacturer guarantees 16% efficient one, then in a real life, it is only coming to 11%. So this is how we have investigated. And then we also seen other effects that are possible for solar power plants. Say wind causing destruction. If we don't install the supporting structures properly, if modules are not mounted in a way, in appropriate testing wind bearing capacities, they will have a destruction. And also we have seen like most of the PV plants installed, there is a front row shade is happening on the second row. So when this sort of shadow falls, what happens is there is a possibility of hotspot problems, like heating of the modules. Of course, like at a cell level, we have a different diodes that avoid this, but still, it becomes a shadow problem, and then the power output would be reduced because of these things. So now, what could be the best solution here is increase this space. Okay, if you increase the row spacing, there are already studies that mention that 3 to 5% of power excess we can get it. But as you keep on increasing this, the social scientists are coming with a problem of land use conflicts. They say like if 1 hectare of 1 hectare typically comes with a 5 megawatt. Like as you increase the row spacing, the land utilization rate is really high. So this becomes another problem. So then we did like, what sort of problems that comes. And then we also accounted for the total risks that are possible in a PV module. So what we observed is the highest amount of risks are due to EVA discoloration. And then we also have encapsulation delamination, 12%. So at different rates, we have like the possible risks that are possible in a PV module or in a PV cell. So we accounted this in a real time, and we just did this analysis. So now, why these are failing is a question. Like we have seen, like a lot of systems are failing, underperforming or overperforming. They're not as guaranteed as the benchmark as industry service provider. So the key problem is, the risks that are associated while planning or while in the operational phase. So these things mostly we design maybe with a short-sightedness. We just don't account for these things. Now, when you see this performance as a critical functionality parameter, so then as per the plan, it should be in this way. But in real life, in the 25 years of lifespan, we never know what could be, what sort of situation the power plant could experience. Because of that, there would be a dip in the performance. Now, if we don't address the performance in no time, then the recovery times could go higher. So this is how if we don't have this approach while planning, definitely we could see the power plants not performing well. Now, if you see this, a low risk, like if you see here, it's just low risk, but we are able to, recover faster. So that means it is a high resilience system. Now here, if you see here, the risk is very high, but still we are trying to address it without no time. So that means high risk, high resilience systems. So And here, if you see, the risk is low, but the time we have taken for recovery is really high. So that means it's a low resilience system. So now if you see another thing, high risk, but it's low resilient. So what could be the best is either you have a low risk, high resilience or high risk, high resilience systems. That could be the best options. So based on this, we came up with a study. Like, we believe that, it is imperative to integrate resilient and sustainability thinking along with systems innovation, considering the technological progress. So why we are talking again sustainability thinking here is, now these power plants are becoming more like decentralized. They're not anymore centralized ones. So that means when you had to account the impact of these power plants in a national level, you need to have an individual assessment that has to be carried out. So that's the reason we wanted to have a sustainability thinking also in the mind. So that's the reason we came up with a concept, framework called Replicate, that unifies conventional performance, life cycle assessment, and techno-economics, where performance is replaced with a resilience performance. That means we'll have a projected issues after a consolidated discussions with the stakeholders of the power plant. Then we come up with this resilience design, a design by resilience or failure-proof systems. And then here, I'll just take you to the case study that we came up here. So we are calling this as a dynamic gray voltaic farm. This is an advanced version of the agrivoltaic concept that we just do it. So where we co-produce crops and electricity from solar panels. So here, we are using solar as a resilient support system for crop protection from various other reasons. Now, how we replicate is applied in this concept. So first, we need to know the stakeholder requirements and their behavior. Second, we need to know how their requirements would affect the system operation. And then we also should know how their requirements would affect the system design. So now we just did the stakeholder survey. What we found is, these grapes have, different seasonal effects. They might be affected with the rain. There's a news clip. And then we also seen that, solar power plants are already facing land use conflicts, and also they have a water stress issues because of the cleaning. And then, while cleaning, they face they has to use different machinery. So now when two different stakeholders are coming together, it becomes, an issue between two different parties. So that's what we call it as a trust, transparency, and traceability issues. So now we have a resilience issue at a design stage, at an operational phase too. So that's where we came up with the concept called blockchain food, energy, water smart contracts. So where we digitalize the entire operational process using digital smart contracts. Now we deploy different sensors as per the parameters that we need to monitor. Then we store the data into a blockchain ledgers. Then we write smart contracts. The smart contracts are like this. Now this is becoming a co-culture or co-production of energy and agriculture. That means they use same land. So now all the commodities they has to be shared. That means, let's say if water is from a farmer side, water has to be shared between photovoltaic operator as well as the irrigation concept. Then the land has to be shared, either it is a lease or long-term land. All these things has to be discussed. And then we also need to have a solar panel should support protective shield during the rain events or hail events or anything that is possible. So all these conditions we deploy as a smart contracts, and then we make this total system to operate as per this written contracts by sensing the weather parameters. And now this is how the conceptual design of dynamic grape voltaic farm was designed. So we see 3 grape plants on the top solar. Then we have a rainwater harvesting. Then the water is collected to the filter. Why use the filter is, sometimes aerosols will be there, so we have to do it. Then we have a main storage tank. Then we also that connect with groundwater. If the excess water is there, it will go to the ground. We refill it here. If no, we can still extract it. Then we do irrigation, we do cleaning. And then we use the pesticides along with the drip irrigation concept. This is the conceptual framework, we got it. But to actually install this, we need different sort of infrastructure. So that is, first agricultural, we need to plant the vineyard. And after that, we need to have a solar plant layout. Then these two should be overlapped. And then we also have an electrical system layout infrastructure. Then we also have a water infrastructure, panel cleaning infrastructure, then the rainwater harvesting infrastructure. So 4 different types of infrastructures that are possible has to be designed very carefully. Now, this is how we designed, the vineyard as well as the solar farm. So what we did is first, we try to take 1 hectare plot, and then, we designed as per the conditions, as per the grape seed growing conditions. Then we found that, total 1458 vigorous wine varieties are needed. They're installed under 266 white trellis. So all the design conditions are given. Now, similarly, considering the land use conflicts, at the same time performance into mind, we try to optimally design the solar power plant accumulation. Then we got it almost like 5040 solar photovoltaic modules. Each module has 100 watts capacity. Then we place the concept like this. The total, all the photovoltaic modules are on the top, grape plants on the top, so that even in the event of rain, they will be safe. So solar panels will act as a shield. And then each white trellis would look like this when you actually install it. Now, the major concern from a solar photovoltaic module side is a hailstorm. Even in the event of hail, photovoltaic modules can get cracked. Because of that, the power could be reduced. So it's called a degradation effect. So we tested this in collaboration with Wari Energies Limited in Gujarat. So we tested for a different hailstorm diameters, 25, 35, 45. And what we found is at different momentums, different speeds, we found that there is a possibility of power reduction at 0.21%. So we accounted even this effect, and we found out the total crop production yields per 1 hectare, and then the energy production that is possible at a DC level, at the AC level, accounting all the issues. And then we did the life cycle sustainability assessment for grape crop as well as the solar crop. So what we found is the grapes grown under this dynamic grape voltaic form will have lower emissions per 1 kg of grape produced when compared to the business as usual scenario. And the same thing with the wine grape variety too. And then we also able to find out that a low carbon solar electricity production is possible because water is reduced, groundwater extraction is reduced, because rainwater is used as a cleaning first, and then it is gone for a drip irrigation condition. So that we accounted, and we did like groundwater extraction scenario, groundwater plus rainwater sharing scenario, depending upon the seasons, if rain is lesser, and then if completely washed by rainwater, what could be the potential. And then we also estimated the cost for it, the unit selling cost, considering degradations, because though we have 0.21% degradation, we went even higher, we went to 2.5%, given other conditions are possible. So we found that the solar cost could be kept it at a lower price, that is 5 rupees to at almost like 9 rupees close to. And then similarly with grape crop selling price also, we tried to estimate it, and we estimated the total cash flows. And then we integrated this with the supply chain, because mostly now, if you want to trade any grapes from any country, you need to have a chemical-free content certificate. Conventionally, this is the certification process that is followed, and in India also we follow this. But this is like, too many stakeholders are involved, too many offices, then it will become a big problem. That's the reason we try to integrate our digitalized blockchain few contracts directly with this software tool, where we just directly integrate GrapeNet here. So then what happens is everything could be online under one umbrella. It is directly grape farmers are linked to the supply chain, and solar operators are directly linked to the grid. So everything would happen virtually. Now, after all these things, what we try to find is there is a scope for symbiotic industrial networks, because we are trying to deploy this in rural areas. So that means there is a high possibility to use these farming sites as a rural electric vehicle charging stations. And on-site wine production is possible because electricity is available there itself. Resin production is also possible because electricity to heat can be converted, and then all other varieties of industries are also possible. And then in conclusion, though we have seen solar as our own case study, but PV alone is not possible to meet our sustainable energy goals. So for that, we also need to create a multifunctional integrated systems with synergies, like how one synergy is shown here, but all other synergies are possible. And irrespective of the shown application area here, replicate framework can be leveraged. Only thing is the type of analysis under resilient performance parameters would just vary. That's it. Yeah. And thank you for this opportunity. And thank you, HKIC and my supervisor.